Hi everyone, welcome back. This is the third lecture of the Data Analysis Summer Preparation Series on Probability. The topic for today is set operation rules. Set operation rules are mathematical equations for set operations. The first one, subtraction rule, is self-explanatory. It's just the not operator, P, and then 1 minus P is for anything that's not P. So we're going to skip that and focus our attention on the next four rules: the addition rule for all or, conditional probability rule for given, multiplication rule for and we'll also derive the base rule. Starting with the addition rule. Or union is the operation for combining both sets, the chocolate or peanut, including the area that overlaps between the two. So anything that's covered in the yellow color is included in the or operation. So this includes customers who like either chocolate or peanuts. So that's people who only like chocolate, who only like peanuts, and also those who like both chocolate and peanuts. The or operation is shown here using this symbol. It's like the letter U. It combines the two areas. So if we have 24 customers who like chocolate, and then we have 16 who like peanuts, when we combine them together, we actually see that there's a little bit of overlap in the middle. So those 4 customers who like both chocolate and peanuts are actually double counted. So what we want to do is we want to combine them together, and then we need to subtract the double counted area, which is the overlap. And then we divide it by the sample space, which is 100, and that's how we get 0.36. To make the addition rule more generalized, so we can use it in any condition, here is the more abstract version of the rule that we just saw. So the probability of X union Y or Y is basically the probability of X plus the probability of Y, and then we have to minus the intersection, the overlap in between. If there's an overlap, sometimes X and Y don't overlap, and so the intersection will be 0. But if they overlap, we'll have to take it out because it's double counted. So here's a challenge for you. The probability of getting either 2 or 3 in one roll of dice using the addition rule. The next challenge is the probability of rolling an even number. So we'll look at the solution at the end of the lecture. Now let's look at the next rule, the conditional probability rule for given. So here's a conditional probability. We want to know the probability that we have customers who like peanuts, but given this condition that they also like chocolate. So this is not just anybody who likes peanuts. We only want to focus on those we already know that like chocolate. So basically, when we look at the sample space, we want to focus our spotlight only on these people who already like chocolate. So given the knowledge that they like chocolate, we want to know how many of them like peanuts. Well, in this new sample space, so the original sample space is 100, so we're not looking at that anymore. This is going to be our new sample space, which is only 24 customers who like chocolate. So given this new sample space, what's the probability of getting someone who also like peanut? So this P is actually P and C. Okay, so it's the union between the two. This 4 customers who like both peanuts and chocolate. And so we'll take this as the numerator and then divide it by the new sample space, which is 24, and that's how we get 0.167. So very important, the condition over here, whatever given condition you have, that will become your new sample space, and the new sample space will become the denominator. So here is the conditional probability rule in more general terms. The probability of y given x, this is the condition that you're given, that will become your new sample space. So that new sample space will become the denominator. And then the intersection, this area that includes both of them, will become the numerator. So the conditional probability rule is basically the intersection divided by the probability of the sample space of the condition. The next rule, multiplication rule, is for and. We want to know customers who like both chocolate and peanuts, so that's basically the intersection over here. Most of the time, the intersection is given, so you already know this. However, what if you don't know? This number is unknown, and you have to calculate it from other known probabilities. Well, we can apply the rule over here. The rule is the multiplication rule. So the intersection between the two, when it's unknown, however, if we already know the conditional probability of C given P, then we can multiply it by the probability of P to get this intersection. Also, likewise, if we already know the probability of peanuts given chocolate, then we can multiply it by the probability of chocolate to get the intersection probability. So how do we know this? Well, this is actually derived from the rule that we have just seen. It's derived from the conditional probability rule. So here's the conditional probability rule, y given x. It is calculated by looking at the intersection and divided by the probability of the sample space. So if we want to calculate the intersection, and this is the unknown, what we can do is we can move the conditional probability to the other side of the equal sign. We can also move the probability of the sample space here. And since we moved across the equal sign, we have to change the division sign to a multiplication sign. And this is how we multiply these two together to get the intersection, therefore the multiplication rule. This rule also works the other way around. You can also use the probability of x given y. And then in this case, the sample space is the y condition, so you will have to multiply it by the probability of y. So to recap, we've seen three rules: the addition rule, the conditional probability rule, and the multiplication rule that derives from the conditional probability rule. And now we're going to use what we have learned to derive the Bayes rule, which is a very important rule for modern statistics. So let's take the conditional probability rule and the second version of the multiplication rule. We can combine them together to get the Bayes rule. So the idea is that sometimes we want to know x given y, but we only know y given x. Okay? How do we get this version out of this? If you only know one of these conditional probabilities and you have to derive the other, which is unknown, how do you do that? Well, you can do that very simply by combining the conditional probability rule with the multiplication rule. So in this case, you see that the probability of y given x is calculated by looking at the intersection and divided by the probability of the sample space x. Well, we also know from the multiplication rule that the intersection can be calculated by the probability of x given y and multiplied by the sample space y. So what we can do is we can just move it up and replace the intersection with the multiplication rule, expand it, and get our base rule. So the base rule is basically derived from combining the conditional probability rule with the multiplication rule. So here is our new base rule. So we can calculate the conditional probability of y given x. If this is unknown, then we can calculate it from the probability of x given y. So which is very convenient because a lot of times what we want is not necessarily available. But if the other conditional probability is available, then we can do some simple mathematical tricks to figure out what we want. So x given y multiplied by the probability of y divided by the probability of the sample space. So see, the sample space probability is always the denominator. Let's take a quick look at the class data set for more demos. So this is a table that you've seen last week. You see A, B, C, and D, and these are the probability for X, not X, Y, not Y. So you can see the intersection, and you will see the intersection of X and Y happens to be A. So it's the probability of both X and Y together. You can also see the probability of y is the entire column of y. The probability of x is the entire row of x right here, 16, 24. And then you will see the probability of y given x is over here. So how do we calculate that? Well, when x is the condition, then we're looking at this, x as the new sample space. And then we'll calculate how much y and x kind of intersection is out of that total. So it's 4 divided by 16, or 0.25. So this is calculated using the conditional probability rule. You can actually take 4 and then divide it by p of x over here. The addition rule can help you figure out this number, and it is the probability of x, which is the total for the x row, plus the probability of y, which is the total for this column, minus the intersection, which is 4 over here, and that will give you the x or y, which is 0.36. You can also apply the multiplication rule to figure out this number over here by taking the probability of y given x, which is over here, multiplied by probability of x, which is over here. The base rule, the probability of y given x, which is 0.25 here, can be calculated from the probability of x given y, which is over here, 0.1666667, multiplied by the probability of y, which is the column total here, 24, divided by the probability of x, which is the row total over here, 16. And that's how you can derive the probability of y given x. All right, so that is all of the rules for set operations. So going back to the challenge I presented in the beginning, the probability of getting both 2 and 3 in one row using the first rule, the addition rule, you will see that when you look at the intersection, basically you're looking at the probability of 2, probability of 3, and you want to look at the overlap between the two. Well, both of them, the probability is 1/6. However, you could see that these events are mutually exclusive in one toss. When you get 2, you will not get 3. When you get 3, you will not get 2. And when you're looking at this pie chart, you will see that none of these events overlap. So, in other words, they're mutually exclusive. So the probability of getting both 2 and 3 using the rule over here, you will see that no matter what rule you apply, you will get a 0 because the probability of getting 2 given 3 is 0. So you multiply anything with 0, you will get 0. And the reason is because these two events don't overlap at all. So getting 2 and getting 3 are two events that have 0 overlap in between. So using the multiplication rule, we can figure out the probability of 2 and 3 intersection is 0. The probability of getting either 2 or 3 will be using the addition rule. So you will have to add up the probability of 2 and the probability of 3. So you will add them together. Each one is 1/6, and then you will have to subtract the overlap. However, because these two events are mutually exclusive, the overlap is 0, so you will subtract 0. And so the answer is 2/6. Again, this is the application of the addition rule. Next, what's the probability of rolling an even number? Well, again, this is really straightforward. Even numbers are 2, 4, 6, and these events don't overlap with each other. So you would just add them up and subtract 0 because we have no overlap, and the answer is 3/6. To get more practices with set operation rules, please go ahead and go to the website and visit the Khan Academy links. You will be able to perform more practices there and get feedback right away on their site. So what did we learn today? We learned the addition rule, the conditional probability rule, the multiplication rule, and the base rule. If you have any questions about this lecture, please feel free to contact me at rachel.chang@mason.wm.edu. I do look forward to hearing from you. Thank you.